Okay, so completing the solution for this question, why is the explanatory variable in temperature? Because I don't think that dissolving times are going to affect temperature. I think that changes in temperature cause changes in the dissolving time. So that means we're explaining the changes with temperature, and the dissolving time is a response to that. So dissolving time would be the response variable, but the explanatory one is temperature. In part B, I was just finding the values of A and B, so I've put the data from my table into the calculator, and in regression calculations I can read off my A and B values, make sure we give them to 3 significant figures. So A turned out to be 5.95, B turned out to be minus 0.08727, so that's 3. Give these to 3 significant figures. If you give them to too few significant figures, you can lose marks. Okay, so put them in the right places in the equation. Okay, the question was kind enough to remind us of the format of the regression equation, but your calculator is probably the best one to use. So your calculator, A and B need to be in the right places. So A is A plus BX, so 5.95 goes there, and minus 0. I've not left enough space. So it's 5.95 minus 0.0873 times X. Okay, next part of the question was interpreting. In the context of this question, we have to interpret the value of B. So here's my value of B. So something is going to increase or decrease by something. Well, okay, B is negative. So I don't want to say, I could do that it increases by minus 0.08, but you're not going to get the marks for that because that's just not sensible English. So we need to pick up that this is a decrease. So I'm not going to say increases. I'm going to say it decreases by 0.0873. So I'm showing the negative by the word decrease, and I don't need a negative sign here. Which is it that's increasing or decreasing by B? So going back to the table, okay, the gradient of B is the change in y every time x changes by 1. So get y and x the right way round, okay? Y is the response variable, which is the dissolving time. So it's the amount the dissolving time is going to change by when x, which is the temperature, changes by 1 degree. So we're going to say that the dissolving time decreases by this value for every increase of 1 degree, I should say, in temperature. And then for the interpretation of A, okay, so this is actually why we can't interpret A, but the question mentions interpretation of A. So what we would normally say is that it's the y-intercept, so it's the value of y when x is 0. So if I actually name those variables, okay, so A, and always give the value of A, so 5.95 would be, 5.95 is the value of the dissolving time when the temperature equals 0 degrees C. Okay, so that would be our normal interpretation of A, but we're told this isn't sensible. And why is it not sensible? Because at 0 degrees C, the water is going to be frozen. So, but the water would then be frozen, so of course the dissolving is going to be impossible. Okay, but that should be enough to get you the marks. And then in part D, we've got to do an estimate for the time when the temperature is 30. So when the temperature is 30 degrees, I shove that value of 30 into the equation that I got higher up the question. So I'm going to do 5.95 plus minus 0.0873 times 30. I'm going to do that calculation. Here it is, and here's the answer, 3.331. So I'm going to give to 3 significant figures, 3.33 minutes. And then at 75 degrees, what's the last part asking me? The last part was where it asked me to explain why the estimate wouldn't be valid for 75 degrees. So I've got to do it for 75 degrees. So we do the same thing for 5.95 plus minus 0.0873 times 30, and sorry, not 30, times our new temperature of 75. So if I can just change my previous calculation, 75, I get a value of minus 0.597, so equals minus 0.5975 minutes. Okay, so this takes a negative amount of time to dissolve. No, I don't think so. So we need to explain why this is impossible, but the dissolving time cannot be negative. So that's showing that the equation cannot be used. Okay, so we've got quite a bit of reading to do here. We've got a gardener, we've got a time, y minutes, and we've got different temperatures, x degrees. So we've got bivariate data with two different variables going on, and we've got a result showing x and y. So this is looking like correlation and regression, and yes, I can see the word regression coming up later. So in the part A, we've got to state why the explanatory variable is temperature. So they've kind of they've told us which one it is, and they've made it x. So the explanatory variable is the one we put on the x-axis, and the other variable, the response variable, is the one that goes on the y value axis. Sometimes this is called independent, sometimes this is called dependent. Okay, so we need to explain why they are this way round. So you've got to consider whether it's more likely that changes in the dissolving times cause the differences in temperature, or whether it's differences in temperature that cause or explain the differences in dissolving time, and you need to write a good English sentence to explain which way you think the causation is more likely to operate. So your solution will be a sentence like this: it's likely that changes in something cause changes in something else. Get them the right way around, and that's that mark. In the next part, we've got to calculate the equation of the least squares regression line, and it even gives you the form of that equation. And of course, this is the clue to what your calculator mode is going to be. So when you go into your statistics mode 6, you're of course going to choose the y equals a plus bx mode. So in your table of values, all you need to do is put the x and y values in from the table of data, and your calculator is going to do all the work for you. So your solution for this is just going to be, from the calculator, state the values your calculator gave you for a and b, but don't forget to quote the actual equation and put your a and b values in the slot. So that takes you to part C, where we've got to do some interpretation in the context of the question, the value of b. Okay? And then in this next one, we're talking about the interpretation of A. So you've got to remember your standard interpretations of A and B, and always use the actual numbers when you do this. So a first attempt at interpreting B, which is the gradient of the line, you have to talk about the variables. So the variables were, if you remember, time taken and temperature. And our kind of usual default interpretation of B is that it's the amount that something increases by when the other thing increases by 1. So get them the right way round, okay? So it's always the increase in y when x increases by 1. But then we might need to just refine that a little bit. So you quote the number, but if it turns out that the number that it increases by is negative, then a negative increase, you wouldn't describe it like that, would you normally? So make sure that you say that go from, you can write down this is the amount that something increases by when the other thing increases by 1, but then you need to turn it into a more sensible sentence, which might involve talking about a decrease instead of a negative increase. Okay, so that's how you word part C1. So you're going to say something increases or decreases, choose which is more relevant, by some amount, so quote the actual number, for every increase of 1 in the other variable. Get the variables the right way around. Okay, and now we're talking about the interpretation for the value of a. So normally you'd be talking about that value itself. You'd be saying this number is the value of one of the variables when the other variable is a particular value. Okay, so in this particular case, that practical interpretation doesn't make sense. So you need to think, firstly, what your normal interpretation would be. So this number that I've got for a would be the something when the other variable equals what value, and then you need to think about what that variable is and think about why that value of 0 in that variable would actually make the experiment impossible. Okay, so decide which variable is going to be 0 for your normal interpretation of a, okay, and then explain why that isn't going to be the case here. So go ahead and do your normal interpretation, okay, and then say the big but is why this doesn't make sense. So this is a bit freeform, but this is just your standard template from your notes, how to interpret A. In part D, we've got to do an estimate of various stuff. The actual important number here is the 30 degrees C. 60 grams and 10 litres have been constant throughout the entire question, but this is 30 degrees C is actually one of our identified variables, which are temperatures, okay, and time. So we've got a temperature, so we're going to insert that into our AX plus B formula to get a time. So in your solution, you're going to say when the temperature equals, state the value, the time is going to be something plus something times something, fill in the numbers and get your estimated time. Now in dotty 2, you've got to be really careful because there are some words that tell you that this isn't actually the normal reason why you might just decide your estimate might be unreliable, because it's not saying why wouldn't we trust an estimate. We're actually saying that the equation cannot be used, okay, and it also has got this keyword show in. That means that we've actually got to do some kind of demonstration. So if you want to show why something's impossible, a good idea is to try and do it anyway. So 60 grams and 10 litres are red herrings. They've been constant throughout the question. We've got this time of this temperature of 75 degrees. We've just done 30 degrees. You do the same thing with 75 degrees, but you need to get an actual value of that, and then that should show us why the equation is just simply not appropriate. So watch out for these. Sometimes it is commenting on extrapolation. Here, the word extrapolation will get you nowhere. You need to do something with this 75 degrees and comment on the answer you get. So you're going to say at 75 degrees, you're going to do your prediction for the value, just as you did before, but then you're going to say big but, okay, and explain why this cannot be valid.